Good afternoon, and welcome to today's Spotlight webinar on Cimatron part analysis tools. Please note that this webinar is being recorded and will be available in a few days. I would now like to introduce you to our presenter, Dan Branch, Customer Support Manager for Cimatron Software. With that, I will turn the floor over to Dan.
What we want to put the spotlight on today is data, specifically CAD data, the geometry that we all import or export in the course of the job, whether that be molds or dies or fixtures or patterns or something else. We all send and receive data. So there's a great advantage to having some tools that analyze data for quality and for problematic conditions. A little time spent up front in part analysis means the best possible start for the job. And knowing that you're working with good data is also an assurance that whatever you need to send out will be in the best possible quality for the next person in line. The good news about translating data is that part quality is as good as it's ever been. For the most part, the days of the terrible tangled IGES are way behind us. The preponderance of solid modeling has led to better geometry, and the translators themselves are also better. Many different types of neutral file translators exist to boil geometric data down to common elements that the next system can then read, many more than just IGES and STEP. And this list here doesn't even include the many types of formats for mesh data. On top of that, many CAD systems offer custom-made direct translators from one system to another. These are typically the best answer for the translations you do most frequently. The only real bad news about translating data today is how often it has probably changed hands. Complex designs and revisions travel around companies and shops worldwide, and that can sometimes cause a degradation of the data, perhaps bad enough to delay the project or even create mistakes in the manufacturing. As a Cimatron user, you have some very simple but effective tools to check and fix the data that you receive. The few minutes you spend up front using these tools will always pay back later on in the project. The one that we recommend you run first is called, obviously enough, Check and Fix. This function checks for several data conditions, but namely invalid surfaces. The idea of a surface being invalid is actually a bit hard to define, as they may look perfectly fine on the screen. But a CAD system relies on a mathematical database, and an invalid format is one of the problems that could result from the translation of the data from system to system. Because the analysis finds no data formatting issues on this part, we have nothing to fix, and ideally this is always the case, but later we'll look at a part where it isn't. So our part has no faulty faces. But next we want to move on and check for a number of other geometry-related issues that might cause some concern. The body integrity analysis function checks the part for 5 common problems. We could check for these one at a time or just run them all at once. Anything that the analysis finds will light up on the part in a specific color. In this case, the dialog shows 5 red X's. So we have at least one example of each kind of geometry problem here. The first part condition that we can look at are the open edges. An open edge is a meeting between 2 faces that is not stitched to solid. An open edge is of no real concern for Cimatron. The system was designed to work equally as well on any number of open or closed objects, which is one of its advantages for tooling design. So an open edge then is really only of interest in that it might reveal a geometry problem that was unexpected. In this case, it would seem that the data translation from STEP has caused the fillet to untrim. And retrimming the face will quickly correct this, so it presents no real worry. The next check was for tolerant edges. And a tolerant edge is not an open edge. The solid is definitely closed at a tolerant edge. But what Cimatron can do is measure the behind-the-scenes variance between the 2 actual surface edges. If you recall, this check was ran using a value of 0.02 millimeters. And the pink areas on the screen are the edges where the actual surface gap is larger than 0.02, but the solid tolerance used was loose enough to knit it anyway. If we were to rerun the same check, but with a smaller value, we would expect to see even more tolerant edges appear. It's expected because no geometry is absolutely perfect everywhere. So if tolerant edges are a normal condition in any data, why are they worth checking for? And the answer is related to what the shaded display cannot show. The system has to display the solid part as it was defined to you. So we only see one edge where the faces meet. The real surface math lies hidden underneath. Only in a very, very extreme example would this really be a problem, so let's take a look at one. This part data was sent as a solid, and so a solid is what you see on the screen. But if we run body integrity analysis, an edge that shows tolerant at a huge value of 1 millimeters is a big red flag to you. And that's what tolerant edge analysis does. It's designed to draw your attention to an area so that you can decide what number is large enough to warrant further investigation. One way of seeing the actual surface math underneath would be to display the U and V curves of a surface. We've done that here, and yes, something is definitely amiss with these surfaces. Unstitching the faces from the solid is the ultimate way to free them from the solid constraints. So here, the solid tolerance of the part must have been so incredibly loose that it was still joining faces that were either damaged by translation or just really poorly created. And we know this example is way over the top, but it's a useful way for me to illustrate the concept of a tolerant edge and why they may be of interest to you. Back at this part, the next color that was left behind by the body integrity analysis was for non-manifold geometry. And like a tolerant edge, this is a condition of a solid that isn't necessarily illegal, it's just interesting. The most common case you will see is when more than two surfaces meet at the same solid edge. In this example, the tangent circles technically bring four faces into the same one edge. And unless this is undesirable for the part, you can generally ignore the problem. This is also the area on the part that was called out as self-intersecting, and for the same reason. Most often, though, a self-intersecting solid is a little different. It looks like a mistake in the design, perhaps a feature of the part that collides with some other wall of the solid. Self-intersecting is really not very often found, but when it is, it always deserves a minute for a closer look, so we check for it. And then the last condition the analysis looked for was called knife edges. This was also a variable. We had to check for part angles that were under 10 degrees. What it found in red can best be seen by sectioning the part. Good plastic part design avoids very narrow areas because they would require blade-like steel in the mold. So often, you may find that a discovered knife edge is really a small mistake in the wall thickness offset or from features that do not completely touch. Either case is basically a design error that should be examined and corrected. Speaking of plastic parts, a value you need for press planning is the volume of the part. This Cimatron calculates in the measuring tool. Volume is 14.42 cubic inches here. An additional measurement shows you the projected area of the part, which is only the surface area viewed flat along the XY plane. This becomes a very useful number when you need to calculate the press tonnage required. The next type of analysis that we can quickly run is wall thickness. Consistent wall thickness is an important consideration for plastic parts and useful information on any kind of part. An adjustable set of range colors helps you understand the result, and the point of maximum thickness is called out on the screen. In addition, selecting anywhere of interest on the part gives you the precise thickness at that point. Given that the typical wall here is about 0.86, the max thickness area, which is at 165, they're about double that and could be prone to sink marks. So these are corners that should be considered for redesign. The next part we have to look at is more imported data, a SAT file this time. As it is more complex, it provides me the opportunity to come back again and discuss the check and fix function. As we said earlier, fixing invalid faces assures that you will be starting the project with the best possible data. Some invalid faces are found here, as well as some other surfaces that are identified as small or unsmooth. The ability to hide and show the different types of problem geometry is built right into the function. So these are the few invalid surfaces on the part. Of course, some surfaces may belong to more than one problem area. Small faces are of particularly interest. The system calls these out because they have an area that is so small that they're totally inconsequential to the part. So naturally, they're very hard to see, although sometimes they appear as lines on the screen. A line-looking surface has length but no width, so it will have no area. Slivers like these cause nothing but problems down the line, so we recommend that you simply delete them while the fix is being ran. Now, even after running the fix, some of the invalid surfaces might still remain. In this case, 4 surfaces are still being identified as problematic. At this point, you really have 2 choices. Often the best one is to be done with part analysis and just get on with the project. Cimatron will always let you move forward with any data. There's no rule that says these 4 remaining faces can't just be left alone and used as is. But the other choice is to spend another minute and take a closer look. If you do see that the geometry has a visible problem that should be fixed, Cimatron has functions to fair or retrim or remake even the most common or complex shapes and geometries. As an example, I'll use a function called fair on a surface that looks like it suffered some sort of data translation issue. Fair only took a second to run and relieve some of the stresses that exist in the data. It can definitely help, and you see this surface looks a lot better already. Maybe good enough, or you might decide if it still needs some border work to be perfect. We still have not explored all of the data analysis tools. Some users may want to look at the curvature analysis of the part. Like the wall thickness analysis, this function has a set of colored ranges And it also lets you browse the mouse around to find very specific radius values on the part. Sometimes this is used to help identify small areas that will need to be inserted or burned with EDM, or even to find what cutters will need to be ordered when the job gets to NC. And then there is long-thin analysis, which looks the part over from the perspective of feature width versus feature depth. It's only a two-color analysis, and the default value is a 4:1 ratio. So the result that it gives is an attempt to illustrate the more narrow and deep features on a part. This is yet another way, though, to get information about the part in the first few minutes that will help you plan for the manufacturing stage of the project. If it is a part to be molded, like this one, these are again areas that will be hard to machine and will likely need EDM or inserts to properly form. We're going to end with a simple function that is really more of a shading tool than anything else. Applying zebra shading on a part is just a way to visually check tangency and continuity from one surface to another. It's useful for show parts, where smoothness is an important factor of the design. A sharp feature edge will bend the stripes, so what you hope to see is uninterrupted flow as the shading lines pass from cosmetic face to cosmetic face. Like all of the other Cimatron analysis tools, it's very quick to run and has some adjustable settings. And that's what we wanted to show you for today on the topic of part analysis.
Okay, thanks so much, Dan. At this time, we will open the floor to questions. Feel free to type in your Q&A box. And we'll take a look at the questions that have come in thus far. Okay, the first question. Will using fair on a surface change its shape?
Yeah, the fair function actually has two tolerances that go with it. One is an edge tolerance and one is an overall kind of interior tolerance. So a part of what it does is to relax the stress in the surface. That does that by changing its shape a little bit. But because you have those two tolerance controls, especially the one at the edges, which is pretty important to keep small, 1 or 2 tenths, you have the full control over how much it might change. And it doesn't mean it will change that much. It's just, that's a measure of how much you'll allow it to change.
Okay, perfect. The second question, when is the best time to use the check and fix function?
Check and fix is a really good function. We do recommend that you use it when you first get the data, kind of like we've been talking about here today. That's the best time because anything that's wrong you fix right up front and you're not working with it, you're not passing it down into other modules like an electrode or something. But you can run it any time. I also tell people that you should run it when you change your basically the module you're using. So if you're done with modeling and you're going to NC, run check and fix. Sometimes there are things that are invalid that that modeling had no trouble with, but the NC doesn't like. Same with creating drawings. If the parts are done and you're doing some drafting, it's worth a couple seconds to run check and fix at that point too. So when you first get the part, and then also before you go into any of the other utilities like NC and drafting.
Very good. Okay, it looks like that's it for the questions that have come in thus far. Thanks so much, everyone. Have a great day.
Thank you.